We've been talking about the differences in isomers, how to identify which type, and their relationships with each other. But we should examine the properties of these isomers. So, let's go back and look at a constitutional isomer. So, constitutional isomers will have the widest variety in their properties. They will have both a difference in chemical and physical properties. So they will react differently. They will make different products if we undergo chemical reactions. They also have different melting points, boiling points, densities, a lot of different properties there. And these can have the widest variety of properties. The reason why is because constitutional isomers can have different functional groups on them. One example of this could be like an ether, such as like a tetrahydrofuran, versus, let's see here, 1, 2, 3, 4, versus some alcohol. This has hydrogen bonding, so the boiling point of it will be much higher. It also has an alcohol versus an ether. Those have very different chemical properties. Or there's some unsaturation on the molecule, and in the form of a double bond. And double bonds have very different reactivities versus a ring, or kind of a saturated carbon, even though a ring has an unsaturation. But they react differently. Next, let's look at diastereomers. These also have different chemical and physical properties. That said, they're not as wide-ranging as the constitutional isomers, because if we have an alcohol, we will also have an alcohol in the other isomer, because all of the bond connectivity needs to be the same. However, we can have some widely varying physical properties just due to the polarity differences in the molecules. As an example, let's look at the polarity difference between something like a cis difluoroethene and the trans version. The cis version will be polar, whereas the trans version is nonpolar. So the cis version should have a much higher boiling point than the trans does. We will also see different products if we perform chemical reactions on the diastereomers, or at least we can. Sometimes we'll lose some of that information, but if we are careful in how we do our reactions, we can preserve some information, and we'll make different compounds from these two different isomers. So while they do have a range of differences, they're a little bit lower in range than the constitutional because we do need to maintain all of the same functional groups. They are just oriented a little bit differently. But that said, both constitutional and diastereomer isomers are much easier to separate than an enantiomer. The reason why is these have identical chemical and physical properties when they're in an achiral environment. Now, most of the time, we're operating in an achiral environment. So that makes enantiomers much harder to separate. Separate or isolate or purify. Some reactions will take something that is not chiral and turn it into a molecule that is, but they're not selective on which chirality they're generating. Take, for example, this alcohol. If we added something over this double bond and it added to the second carbon here, some group, that would generate a chiral product. But which chiral product it would generate is dependent on which side it approaches. So if it approached from the top side, it would generate one enantiomer. If it approached from the back side, it would generate the other. And since both of these in an achiral environment are equally probable, we often make racemic mixtures. That's what we call them. And a racemic mixture is just a 50-50 mixture of the two enantiomers. Sometimes this isn't a problem, but if we want just one enantiomer, we've already thrown away half of our molecules, and we have to try to purify them, and purifying them is a lot harder than the other kinds. So what can we do to actually purify these? Well, somehow we need to differentiate the two enantiomers. And I said they have identical chemical and physical properties in an achiral environment. So if instead of using an achiral environment like we typically have in the laboratory, we could change it to a chiral environment. So there's a few ways of doing this, and one of the common ways is to use some chromatography. Now, we recently did a laboratory that is on chromatography where we separated carotenoids and chlorophylls out of spinach. And this was easy because they're not even isomers of each other. They're completely different molecules and they have vastly different properties. So we could use just alumina as our stationary phase. If you, however, you're trying to separate enantiomers, you need a chiral stationary phase. So you need a special solid to put in your column. And if the stationary phase is chiral, then one of the enantiomers will interact with it better than the other. And that provides a little bit of separation. And you can take advantage of that to isolate one and then the other isomer by running the column. And you can even do this some with different machines that have a chiral stationary phase. And that's pretty common in order to evaluate what type of compound you made. Now, if we would like to avoid making a racemic mixture, there's a couple of things that we could try. You can start with a chiral or a pure compound, so just one enantiomer. And you might say, well, how will I do that if it's difficult to isolate that? Well, a lot of biological molecules are chiral and they exist with just one enantiomer. Proteins and the amino acids that make up proteins are one of those molecules that has just the one enantiomer. So you may be able to start with that. You could also employ a chiral catalyst. So the catalyst that we would use has chiral groups on it, and that can influence the reaction one way over another, because now there's a difference in how the molecule that's being reacted upon would interact with that catalyst. It's also possible to use a chiral auxiliary, although this is probably a bit less common than the chiral catalyst, or starting with a chiral compound. In this case, you would use a molecule that is chiral and pure, and you just add it to the reaction mixture. But it is inert relative to the reaction conditions. So it does not react with your starting material. It's not interfering with that. And in that case, you can make the environment chiral by dissolving this chiral compound in there, and then it influences the environment. It changes it from an achiral environment into a chiral environment, and that can influence reactions. Now, you'll probably have to use a fairly high concentration of the chiral auxiliary, but that's something that you can do. And a lot of times you would use some natural product that's easily obtained to act as your chiral auxiliary. One other method of actually separating chiral compounds or getting just one is to actually convert them into a diastereomer. So you convert it to the diastereomer, and then you can separate the two compounds, because diastereomers have different chemical and physical properties. Then you take advantage of those different properties, separate the two compounds, and then undo the conversion. And now you've isolated the one enantiomer. One thing that enantiomers are well known for, and I should mention it because it is a property of them, is that they are optically active. And that is, they will rotate plane polarized light. So if I have my light and it's all oriented in, let's say, a vertical direction, if I let that light go through a solution of a pure enantiomer or a pure chiral compound, it will rotate that light either to the right or to the left, whichever isomer you have, it could rotate it one way or the other way. And if it's pure, you can, you'll see it only go in the one direction or only go in the other direction. If it's racemic, which the 50-50 mixture, the light will not rotate because one is trying to make it go one direction, the other one's pulling it back. And if they're in equal amounts, then it will stay vertical. And it will appear as if it's not chiral. If, however, you have an excess of one of the enantiomers, it would rotate light in that direction. And you can calculate how much more of one compound you have versus the other, and then report that number. However, now that we have other methods of determining the two compounds, specifically you'll use supercritical carbon dioxide and a chiral column. You'll just separate the two compounds and then you can report a percentage of each. And that's a lot better than trying to figure out based on how they're rotating light. So if you're doing a lot of work with enantiomers, that's how you would prefer to do it. So this is about the properties of isomers, and you'll see that we have a different way of isolating each one of these different isomers, starting with constitutional, which are much easier to separate often. Diastereomers still possible, and enantiomers much more difficult, but we have developed ways of doing it based on taking advantage of some of their properties. So, thank you for joining me for this video, and we'll see you in the next one.